Hi folks, today we're doing a few demonstrations to show the existence of atmospheric pressure. But before you watch these demonstrations, it will be better for you if you read chapter 18 of the textbook or watch video number 38. As can be recalled, the Earth is surrounded by a layer of air that is called the atmosphere. Of course, we know air has mass, and anything that has mass will exert a force on the surface of the Earth due to the influence of Earth's gravity in it. The force that is exerted by the atmosphere on the Earth's surface is calculated to be 101.0 kilonewtons. Translated into pressure over 1 meter squared will be 101.0 kilopascal. In layman's term, what does that mean? Means that if we build a box 1 meter squared and we fill that box with 11.0 tons of material, say sand or molten iron or something like that, the pressure that that box will exert on anything that is lying on will be the same as atmospheric pressure. That's a lot of pressure. 11.08 tons of something fitting in that box there. That's the pressure that we are all experiencing from the atmosphere. But the question can be asked is, why is it that we do not feel crushed by this pressure? The answer to that has to do with us being adapted to living on the Earth's surface. It is said that the pressure that is exerted by our blood and other tissues of the body is equal and opposite to that of the atmosphere. And that is why we don't experience this squeezing effect. Today we will be doing a number of demonstrations to show the existence of that pressure. The first one involves the famous crushing can experiment. Here you see me having an empty pop can. We'll fill that with a certain amount of water, about 20-25 milliliters of water. We'll turn on this hot plate here, and we allow all the water to become steam. And after all the water has become steam, we'll take this using this pair of thumbs here, right? And we'll invert it into this bowl with cold water and observe what happens. So next, that's what we'll do next. So we'll start this experiment up first by putting in that water there. And we turn on the hot plate there, so you come back later and see you. All right, all the water has been changed to steam. So this is what we'll do now. See? The can has been crushed due to atmospheric pressure. We will explain that in due course. We shall now try to give explanations for the observations that you made during the previous demonstration. We first of all start by explaining why pop can was crushed. It is said that in any open system, such as this pop can here, the pressure on the inside is the same as the outside. Atmospheric pressure is acting inside as well as outside. Inside the can, it is a bombardment of the air particles against the inner walls of the container that is able to suppress the atmospheric pressure. To show that an atmospheric pressure was present in that can, we had to eliminate the gas particles within the can. One way of doing that could have been to seal this can and subject the can to a very, very low temperature where all the air particles could have condensed. If that had happened, there would have been no gas particles to withstand the atmospheric pressure, and one would have seen the can implode before our eyes. But that would have been very difficult to do, because to condense air would have necessitated a very low temperature. So what did we do? We tried to replace the air by water vapor that is much easier to condense. So what did we do? We placed some water into that can and we allowed it to boil. As it was boiling, it was changed into a current of steam. As the steam was coming out of the can, it was taking away gradually all the air particles that were inside there, until eventually all the air particles were out of the can. Even the steam inside there, as is happening there right now, is exerting a pressure that is equal and opposite to that of the atmosphere. But if you can get rid of the steam by causing it to condense, then there will be no gas particle inside to withstand the atmospheric pressure. And therefore, if the can imploded, we could say that, oh, there was a pressure outside. In this case, when we cool the gas or you allow the water vapor to condense, we have to seal the upper end of that. That is why we will invert it into the bowl of cold water so that no air will be allowed to enter from the top. If we did it just like this, just took this and put it here, nothing will happen because the water vapor will condense, but air will rush inside to fill it back again. So what we'll do now, we'll repeat that experiment again. We try to condense the water vapor, create a partial vacuum inside, and see whether or not there was an outside pressure, because there'd be no pressure inside. So let's do that. See? Look. The can was crushed, all because of the existence of an atmospheric pressure. I hope that was useful. Thank you. In this other demonstration here, we do something similar to that as what we have done with the pop can. We put a certain volume of water inside here and allow it to boil for a few minutes, or allow it to boil until all the water has been boiled off from there. Then, instead of inverting this over cold water, we will instead don't do that, but take this piece of plantain here and stick it over the mouth of this Erlenmeyer flask here and allow the system to cool, and then we'll absorb. So we allow that to go for a minute or two, and then when it's about to finish, we'll come back. We can now see that nearly all of the water is about to be boiled off. We wait a second or two more until all the water has been boiled off. Then we'll remove it from there and then insert the piece of ripe plantain into the neck of the Erlenmeyer flask. Okay? So here we go. Here you are. Put this here. And we put that inside there. And then we allow the system to cool and observe. You accelerate the cooling a little bit more. Right. There seems to be some action going on there. So watch that attentively. Not doing anything with it. You can see that the piece of ripe plantain is being sucked into it. Boom. Good job. All right. Next, we'll give an explanation of what happened here. Okay? As in the case of the pop can, we wanted to create the same effect. We wanted the air particles inside that Erlenmeyer flask to be removed. So we boiled a certain quantity of water to create a current of steam long enough to remove all the air particles from there, with effect of creating a partial vacuum. But only in this case, we will not invert the Erlenmeyer flask into a bowl of cold water. We left it just like that, and then we inserted this plantain into its mouth. Now, why did this plantain get sucked into the Erlenmeyer flask? And the explanation is this. So I'm going to demonstrate this one more time for you. While that is happening, I'll explain to you why it got sucked into that Erlenmeyer flask. Okay? So We'll repeat the experiment one more time. You can see that the water there is about to boil off. So second or so more. All right. Now, when you do that, you have to do it, you have to seal it well and proper so that no air gets inside. What is happening here, again, like the pop can, the water vapor inside here condensed. And when it condensed, it created a partial vacuum. And because there was an atmospheric pressure was much greater than the pressure within the Erlenmeyer flask, and it was pressing down on that plantain there, and that is why the piece of plantain was sucked into the Erlenmeyer flask, okay? Because of the presence of an atmospheric pressure. Partial vacuum was created there, and air always wants to flow from a high pressure to a low pressure. Only in this case, it had to press the plantain down. And that's another demonstration to show the presence of atmospheric pressure. Hi, this third experiment here is my brainchild. What I have done is this. I took a hypodermic needle and I passed it through this stopper here. On the other side of the stopper where the head of the needle is, I inserted a rubber tubing and I glued it down firmly. I did that because I want it to be airtight. The other end of the rubber tubing will be in this beaker of water here. Now what we'll do, as we've done before, instead of using an Erlenmeyer flask, I'll use this volumetric flask now, and I insert the same volume of water, 50 milliliters of water, and I put it on this hot plate here and turn it on. Okay? Now when all the water is boiled off, all the water has been changed into a current of steam, I will take this off and quickly insert the stopper here very firmly so that it's airtight, and we allow the system to cool and absorb. Okay, so we'll now start this experiment up right now, and then we'll come back afterwards when all the water is about to be boiled off. As you can see, nearly all of the water is about to be boiled off. Maybe you can wait a second or two more until all is done. Then we quickly take it off the hot plate, okay, and then insert this stopper firmly into the mouth of that volumetric flask there, and then we'll observe. Now quickly we'll do the process. We can see that water is now coming through that hypodermic needle, through this rubber tubing here, into this flask here. See, once I did this at my home school, C.W. Jeffries Collegiate, and I invited some of my colleagues from the science department to observe this part of it. And they were somewhat awe-stricken by what was happening there. Of course, I didn't show them what happened before. I'm sure had I showed them that, they would have figured out exactly what was happening here. Isn't that cool? Isn't that cool? Look, water is turning pink, and all of a sudden you see water is moving from that container there into this volumetric flask. Who would like to explain to us why that is happening? Okay, in the meantime, you can figure out what is happening there. So, in the meantime, I just want to say hello to my friends. Stay safe. How do you think we can get this thing to stop? Anyone has any idea how or when this water will stop coming through this tube here? Of course, some people probably say when it's all filled up. Some people say, okay, if you remove this hose from here, let's see what happens if you remove the water tubing from that. Or you want us to leave it like that until it stops on its own. Why not leave it like that until it stops? So try to figure out why that happened and why this water here turned pink. Okay? We shall repeat the demonstration that we did before in an endeavor to explain the observations that we have made. Like we said, we use a hypodermic needle and pass it through this rubber stopper here. And then we took the back end of it and we inserted it into this rubber tube in here, and we seal it off to ensure that it was airtight. Then the other end of the rubber tubing was placed inside this beaker of water here. And finally, what we did, we placed a certain minimum volume of water onto this hot plate here, and we boil it. Why we place a minimum volume of water and boil it was to ensure that the current of water vapor, what we call steam that was coming out there, was good enough, the amount of steam that was formed was good enough to remove all the air particles as it traveled outward like that, okay? And then finally, when all the water was boiled off, we then remove this from here, and we place this rubber tubing into the mouth of the volumetric flask here, and then we cool the system. So we shall repeat this experiment now. So we place this again onto the hot plate there, and until all the water is boiled off, and then we shall come back and show you what happens next. Now that all the water has been boiled off, we shall now take the rubber tubing and insert it into the mouth of this volumetric flask here, and then allow the system to cool and observe. You gotta go. Now you can see, come up close. You can see that water is coming through the hypodermic needle. Now, what is the explanation for this? Why is water coming through that needle there? The whole objective, we said, was to remove all the air particles from there and allow only water vapor to remain. Why we wanted only water vapor to remain, as we did in the previous experiment, was to allow the eventual condensation of the water vapor to create a partial vacuum inside here. So we wanted to create a partial vacuum here. How did that happen? Because as the system cooled, the water vapor inside there condensed and created a partial vacuum. Now the pressure inside there is less than that of the atmosphere. So atmospheric pressure that was acting in every direction, sideways, up, down, was pressing on the surface of the water there, as the case as is still happening there right now. And that is what is pushing the water through this rubber tubing here into this flask here. Okay? Isn't that cool? Water turning pink. Why is that so? That's a top secret. Ask your teacher to explain that. So this experiment is showing here the existence of atmospheric pressure. Okay? You created a partial vacuum inside here. And the only thing that would have caused this water to move inside here, it was the atmospheric pressure that was pressing that there and making that. Same thing happens like if you're drinking a soda using a straw. As you pull into the straw, you're creating a partial vacuum, and it was the atmospheric pressure pressing on the pop can, right? That is in the pop into your mouth. So atmospheric pressure has lots of applications. Your vacuum cleaner works on the same principle. When you use your vacuum cleaner, you're really creating an area of low pressure just over the dust particles on your mat that you want to clean. And when you create that partial pressure there, it is the atmosphere that is pushing all those particles into your vacuum cleaner. But I hope these demonstrations were useful to you to make you understand that there does exist an atmospheric pressure. Okay, well, thank you for listening.